Okay, welcome to this lecture 3 in system identification. I will mainly speak about the linear least squares regression. And it is very common to define a linear equation as follows. So, assume given data matrix Y over some output equal to a matrix X also with known quantities or parameters times a matrix B over unknown parameters, regression coefficients, and plus say an error matrix where this one is assumed then to be mentioned with n rows and r columns. The known it is in the literature, some people are defining the variables in y as the regressed variables. Usually we assume that the number of observations n, or this number of rows, are greater than the number of columns. We assume like this. And this data matrix X is then sorry, I wrote an error. Let me speak more about this one. I should have times R here. This is a matrix of regressors. And this inequality in number of observations or rows in those two data matrices be greater than the number of R, like this. B, it could be a matrix, but very usually a vector with unknown parameters. And E is an error matrix. In the numerical linear algebra, usually a different equation is studied. So remark numerical algebra. Literature. Equation AX equal to B is usually, it's more common to use this equation than shorter model. Let me take an example of, or two examples for how to define such a matrix. Consider a simple steady state system. With no dynamics. Here we have a control input U at time k, observation I at time discrete time k. And maybe some noise influencing the same system. And we assume, I have said, steady state with a yk equal to uk the noise. I remember this is the general state space equation where we have states goes down to the simple. And if we transpose here, and assume that we have given some observations, but UK for some observations from k equal to 1 up to n, then we may find such a matrix equation. Data. First, simply transpose this equation. So from 2 we have at yk transpose, then equal to E transpose plus A transpose. And then at the first observation, we have that time 1 transpose to U1 transpose like this. And using all known observations down to k equal to n. So simply we have n equations, this type. Close. Now we can collect all equations in this matrix equation 1. You may write data matrix Y equal to I1 transpose, I2 transpose, then data matrix consists of the inputs, U1 vector transpose in the first row, and U transpose in second row, the last. And then the matrix of unknown coefficients is this E matrix then, or the transpose. It will be like this. Let me take a second example. Here, this is a linear, given a linear system. You see, least squares regression may also be used for more non-linear functions. If we have some observations of inputs and outputs, and we want to find the equation for a known characteristic. Let me take a second example. Fitting a polynomial to data, non-linear polynomial in this example. Let me do my system. Here I have some inputs, say x here, x at discrete time k. Output y at time k. I have arrows here. Here, this could be a valve, for instance. Opening of a valve, and it could be the flow out of this valve. This valve characteristic may be a non-linear, and it may be. So here I think about yes. Here at some discrete time, say from 1 n, and suppose that the data is a non-linear function like this, that we want to find this non-linear. Have y1 here, xn here, x1, 2. Here then. This. And suppose that we assume that this curve could be fitted or approximated as a polynomial. By k at discrete time k be approximated as a parameter a1 times x in an nth order polynomial at discrete time k plus a2 then x in power n minus 1 at discrete time k plus dot plus, I need to take away this, plus then the coefficient a n times x is a nth order polynomial in general, and plus a coefficient here, say then n plus 1. That general polynomial, and let us use our data to find the coefficients in this non-linear polynomial. That is the problem, and this problem may be solved by using a least squares regression technique. With data xk and yk, a number of discrete time instants. 1 2 to n. We do it in the same way as we did for this steady state system. And here I will assume that y is a scalar and x also is a scalar here for simplicity. Then we write that yk a vector, row vector with the regressors x k in x1 dot 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 xk and 1. If I put 1 there and multiply this row vector, a column vector with the coefficients in the polynomial, a1 dot down to n down to the last coefficient an plus 1. And using all n observations, we have a matrix equation y equal to x times b plus e, where this data matrix y is then simply equal to output at time 1, output at time 2, and to the last one. And this matrix X with regressor variables. Now, this row, all n rows, but with different time instance k, from 1 to n. Then. x1 in power of n over n minus 1 dot dot down to x at time 1. Simply 1. The second row, x2 1 dot 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 down to x2 and 1 dot 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 down to the last row, x n power of n. And 1 there and 1 this. So remember, there is this entire columns with ones, and this error matrix is then simply I could have plus some error here, plus e at time k. And then the matrix E with errors is simply taken from it. The problem now is to find the unknown parameters. That is the least squares problem. Least square regression problem. Given data matrices, y x or given known data matrices y or x, and as they have used in numerical mathematics since the World War II. There was published a lot of papers where instead of y, they used an equation like this, unknown a and b. Actually, they study the same problem. The first technique is the so-called ordinary least squares technique. All this problem. Going back to Gauss it is said that it was a paper in 1809. But that is a discussion around that. This technique is I will call it ordinary least squares solution. I will solve or derive this result in two ways. This method 1 is the more mathematically correct way of deriving. You see it? Assume that we want the problem is to given y and x, find b. So I should written given data matrices y and x, find estimate b. Here b is a vector with unknown parameters. But in general, this b may also exist. Minimize the error. Suppose that we are defining an objective, which is a function of this error y minus x b. It also is equal to this error matrix. So, of course, this will be a vector. If y is a vector, then this error will also be a vector. And then in numerical linear algebra, norms of size of a matrix or vector is measured very often as the Frobenius norm. So looking at the norm, matrix norm of this error, those two bars represent a measure of the size of this vector. The most common norm in numerical linear algebra is the Frobenius norm, and this one squared. The Frobenius norm of a matrix is simply equal to the sum, the squared sum of all elements, this vector E matrix. But simply this one may be written as y minus this vector y minus xb. This is a vector. If I transpose this vector, then I have a row vector and multiply with y minus xb. Then I have a scalar valued measure of this vector. And this squared here, and also we have squared. So let me multiply out all elements here. Y transpose times Y minus Y transpose times minus XB, 4 parameters. And I will want to minimize V, the problem. Minimize. This scalar valued function with respect to WRT with respect to this matrix V. From optimization, we know that in the minimum, the derivative of this function will be equal to 0. So I can sketch this scalar valued function V as a function of B. Of course, in this figure, B is only a single parameter. But this function would be something like this, since I have squared here. And in the minimum, here, we will have the ordinary least squares regression, OLS. And exactly in the minimum, derivative, dv x to b would be equal to 0. So in order to solve this problem, it's a good idea to take the derivative of this respect. And in order to calculate the derivative, I multiply out all terms here first. So, as I said, Y transpose Y is the first one. Plus Y transpose times minus X. This. And we have the transpose minus XB transpose times Y. And XB transpose is simply then B transpose X transpose. That is the transpose of the product of X times B times Y. Plus then, because minus minus is plus, and then B transpose X transpose. And the reason, remark, if we have a product of two matrices, say A and B, we want to transpose this product. We have to reverse the order. This is equal to transpose. So I use this rule. Remember also, the resulting value V is a scalar. And then if this is a scalar, then all those four expressions would be scalars. So Y transpose times Y is a scalar. This is a scalar, and this is a scalar, and this one. And since we may simplify two first terms in there as minus of this one. Because if Y transpose XB is a scalar, and if we transpose this one according to this rule, then the transpose of this one is equal, and the transpose of a scalar equal to its scalar. Yeah, so we have that this scalar value function V is equal to Y transpose Y minus 2 Y transpose X times this unknown matrix B plus a second order term here, B transpose XB. Now, we have to go for taking the derivative of V with respect to B. dV, dB. No B's in this term, so in this one then the derivative is equal to 0. But we have a linear term in B here. The derivative of this term with respect to B is in fact the transpose of the matrix in front. So it will be equal to minus 2 X transpose Y. And according in the appendix, the lecture notes, I have some rules about derivatives. Rules from appendix. This is appendix B. You have to have knowledge about 2 rules. One rule for taking the derivative of this one, and one rule for taking the derivative of this second order term. You see, if you have take the derivative of a product A times X with respect X, and this one is equal to A transpose. And if we take the derivative of a product, so like X transpose, say Q times X, or some matrix Q, taking the derivative of this quadratic form, back to X, we have 2QX. This rule is very similar to standard mathematics. Oh. And then the derivative of the last squared term here, plus X transpose X times B. And the solution is given when this derivative is equal to 0. This proof a little bit lengthy, maybe. And then ordinary least squares solution or estimate. Yes. I will use BOLS to indicate this one. Now, of course, this number 2 goes away. Putting this term on the right-hand side here, and then we can invert this one. So here we have an equation X transpose X times B equal to transpose Y. Solve this one by multiplying from left with the inverse of this one, if the inverse exists. And we have this solution. First, transpose Y. If X transpose X invertible, or in mathematics we say that this one is non-singular. It's only another word of invertible. And also we then know that the rank of X transpose X could be equal to R, the number of columns, a full rank. Remember, X is in general a rectangular matrix with N rows and R columns. This is the ordinary least square solution. Useful. I wrote method 1 here. Let me, before closing, simply find this solution more simply by direct solving. Look here, method 2. We have given a matrix equation. And solve for B. If x is square and non-singular, we could multiply with the inverse from left. We will have B alone here and we can solve. But as I said, X is a rectangular matrix. But we simply multiply from the left by X transpose to define the so-called normal equation. That is X transpose Y transpose X times B. Since the error matrix is known, I simply skip the error term here. I could the discussion with having an error term here also, that is X transpose times the error matrix or vector E. But since E is unknown anyway, for simplicity, I skip the error term. Then we multiply from left with the inverse of this one if the inverse exists. Hence, the OLS solution is then B OLS equal to the inverse times X transpose Y. This way of deriving the ordinary least square solution much faster. You arrive at the same equation. Okay, thank you. Break.